All right, so before starting your derivation packet, we need to talk about kind of a little bit more of, first of all, just the theory kind of what's going on here when we're looking at the electric potential for non-point charges and the types of problems you're going to see. Well, like I've mentioned before, you're going to see problems that look very similar to what you did last unit with the electric field. There's some benefits to this. The first thing is it gives you practice on what was going on last unit, so if you struggled a little bit with that, you're going to get a chance to do it again. Although I would definitely strongly suggest that you've completed the previous derivation packets before starting this one, because this doesn't go quite as in depth every time, because this is more focusing on the relationship between electric potential and the electric field is kind of what this derivation packet's all about. But it does give you examples for like extended objects where you could do the electric field due to little tiny slices, or that you can use Gauss's law and so forth. So these are some of the typical shapes that you're going to see. You're going to see rods, cylinders, things along those lines. We're going to see more coaxial stacked cylinders, coaxial spheres. So basically when they're all on the same axis, or concentric spheres, coaxial cylinders. You'll see sheets. You're also going to see like parallel plates, those parallel sheets. So that will make those parallel plate capacitors. You may see rings of charge, either full rings or partial rings. And you're definitely going to see spheres. So the reason that in particular these three shapes are kind of the most important is because we tend to make capacitors by maybe putting like spheres inside of spheres, or sheets above sheets. That makes a capacitor, or like a cylinder inside a cylinder. So the other half of this unit, this is electric potential and capacitance. So these are capacitors, and so therefore we're going to build on everything that we do here with potential, and then add in capacitance, because potential and capacitance are very closely related to each other. Now, there are different ways to solve these problems. Many of these can be solved with Gauss's law or with the electric potential, but only in certain cases. So, for example, if I wanted to look at this rod, if this was a finite rod here, then unless they specifically tell me to ignore edge effects, I have to assume that this electric field points out kind of something along these lines. That's not very good drawing, but close enough. And basically, if I'm not ignoring the edge effects of this rod, then what happens is at every kind of point along this rod, the electric field points a completely different direction. Remember, this radiates out 360 degrees. Wrapping around the rod. If I were to look kind of at the end of the rod, the electric field at the end of the rod behaves kind of like a hemisphere type idea. If you were to do kind of like a shape for that, like a point charge. But then in the middle, you'd assume that, oh well, they're still not going to be radiating out in the same direction as you wrap around. They're not going to be parallel along a particular line. So you can't really even represent this as a cylinder with like two hemispheres for like Gauss's law. Because it's not going to be the cylinder areas in here. If I try to do a cylinder, you know, my DAs are always going to point straight up, but then these electric field lines are going to point in different directions. So you won't be able to use Gauss's law for that. I mean, Gauss's law still applies. But there is no single Gaussian surface that could be used to actually represent that. Even if this rod was semi-infinite and like this side went on for, you know, forever, you wouldn't have any, your edge effects would become minimized. It would become approximately parallel as you got towards infinity, but you'd still have problems on this end. Now, if it is an infinite rod, or it's very, 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 very long, okay, then you can assume that your electric field becomes not uniform, because uniform means equal in magnitude and direction, and this is not uniform, but it becomes symmetrical in a way so that if I wanted to say find the electric field at a point at some radius from the rod, I could use a cylinder to represent that. So in the cases where you can't use Gauss's law, and it is a nice common shape type thing that we'd be able to do, then if I wanted to find my electric field at some point, whether it's here or off on the side or dead in the middle, then I can always assume some coordinate system and say maybe x equals 0. I can take an infinitesimally small slice here, dq, give it a distance dx that's at a position x, and then if I was looking for the electric field's a vector. So if I was looking at the electric field at this point, I'd have a vector dE here, and then I'd have a dx component and a dy component. But when we're looking straight for potential, potential's not a vector. So first of all, I can't draw an arrow for the electric potential because it is a scalar value. But if I did want to find dV, or the potential at this point, then basically what I could do is I could find the dV at that point due to dq, and then I could set up my integral assuming that I have a point charge here. And so the electric field of a point charge is kq over r, the electric potential. So then if I wanted to have, I'd have dV is going to be k dq over r. And then I can then go and sub in an equation for dq based on the linear charge density, whether it's uniform or not uniform. R would be this value right here, so I can then set up a triangle to relate r and x, and I'd integrate along x from x equals 0 to say x equals L. A ring of charge would be similar. We've kind of seen those where basically, you know, you have some sort of like angle theta here that you go between, but if you were taking kind of a slice, you'd still have your little slice dq, but dq might have like a little thickness like ds based on its position, and then it would be at an arc length s that is maybe related with some other angle phi, and then you would integrate essentially, you know, from this point to this point. You could convert it into angular terms with using x equals r theta, and basically treat this kind of as like a line of point charges that's curved. When we do the sheets you have to be really careful about, especially when you're looking at a parallel plate, and that's kind of be one of our new cases, is because if it's just one sheet, then you'd assume that the charges are basically equally distributed on like the top and bottom of the sheet, and then all across the surface. So then you're going to have some charge densities, lowercase sigma here, that would be q over the surface area. And you would have to make sure that you included like both sides of the sheet. This was one of the ones, we did this one for electric field. I could either represent it like with Gauss's law, with like using like a little rectangular prism here. And I've considered that the electric field would go out in opposite directions. And if this was a very large sheet compared to whatever radius r or position y or whatever that distance is from that point, then I can assume that it's uniform and I could ignore edge effects, which is really what you're going to mostly do, is ignore the edge effects of your sheets. And like I said, they'll say either it's an infinite sheet or it's large, much larger compared to this distance r, so that way you can basically ignore the fact that it is going to radiate out weird angles and so forth. So then you can just consider the top and bottom. And like I said, the way we did this in the homework, in the video kind of example, I think it was on the PowerPoint slide, is you had this cylinder that intersected the sheet going above and below, and then this would be your dq, and it would have its own little area, dA, associated with it. Then you say, well, sigma is dq over dA. And then you end up finding that the electric field at one of these points is going to be basically the ratio of sigma and E naught. So it's going to be basically dependent on that sigma. So the big difference this unit is, since we are going to be looking more at capacitors, like we're not often going to do just a single sheet in the end. We might start with a sheet, but then they might go, okay, well now let's put another sheet here, and this one's oppositely charged. This one's a negatively charged sheet. What this does is it changes the distribution of charges, because your charges on the top of the sheet are basically going to move to the inside of the sheet, because what's going to happen is your negatives are going to get repelled away, and your negatives that are on this side are going to get attracted to the top side of the sheet. So then generally what we want to do is we want to look, basically all of your charges are therefore going to be on the inside layers. And then we actually do end up with a uniform electric field inside of here. And so you're going to behave a little bit differently. We generally don't do the electric field at a point with just using the charge distributions like this as often, just because the geometry is more difficult in 2 dimensions. But it still does work. I think there is an example of that. We did the electric field due to like a disk by assuming rings that got bigger. So you might see something like that again. But in terms of like looking at parallel plate capacitors and so forth, you're going to do the same kind of thing. Now, if they say that you can ignore edge effects, then this method works exactly the same way as it would for adding another sheet in. If it says you cannot ignore edge effects, then basically it gets more complicated, and you probably have actually a thickness, and these are not then thin sheets, and so you actually have a thickness here, and then you'd want to put your Gaussian surface kind of inside. So you'd still have a DQ, but you wouldn't want to catch you don't want to catch the top of the plate. You only want to catch the inside of the plate, and then the bottom. And you'd assume actually the DQ would technically be here on the surface, and it'd be on the surface here of this positive charge. So you'd have, but your surface area here for your Gaussian surface would be here, and then just the section that actually intersects that outside part of the plate would be where your charge is. So you'd assume that all of your charges are therefore like on the surface of that plate. And then you could do that. And then if you wanted to, you could do it for the opposite plate. But the opposite plate would basically do the same thing. It would just be having a negative charge. And then looking over here at, you know, something like the spheres, we know that the electric field, as long as you are at an R that is greater than R, is going to be KQ over R squared, okay? When you're outside of that sphere. So if I was outside of the sphere and I knew what radius I was away, I know that I can treat this whole thing as basically acting like a point charge that was essentially located at the origin of at R equals 0. If all of my charges at R equals 0, this blue shell would have the exact same electric field at R as if all of the charge was at this point. So we can assume that that behaves. So therefore I can say that, oh, well, I know that since E is equal to negative dV dx, that if I were to take the derivative of this, then what's going to end up happening is my, I'd have to integrate. If I go to integrate, I'm going to end up with KQ over R for V. As long as I'm outside of that sphere, then I can use that relationship because of the calculus relationship here between those values. But a lot of times what you're going to see is, once again, one of these spheres might be an insulator, and so therefore it can have a charge distribution, and that's where Gauss's law comes into play. Is if you're not outside of the sphere at a point and you need to find the, say, electric potential there, or R is inside of here, well, then you're going to have to draw a Gaussian surface, and like said, and with that Gaussian surface at its radius of R, you're going to then find the electric field, and once you know the electric field, you can use this relationship to find the electric potential. So if you can reasonably treat your object as a point charge, then we know that the potential of a point charge, well, I guess this one technically, is going to be V equals KQ over R. or a sphere outside where you're assuming that it's basically a radius here, then well, if all the charge was here, then I can basically treat my sphere as having the same formula as a point charge as long as you're outside. We also know that for a parallel plate capacitor, we know that our potential is E times D. Okay, so that's actually a set formula that we know for all parallel plate capacitors. So this is something that you could pretty easily derive, and it's because the electric field's uniform that is going to allow you to use that formula. So if you know a set formula, that's good. But then if you have anything else that's not one of those set formulas, so basically KQ over R or E times D for your potential there, then you're going to have to use essentially one of these two methods, either integrating along the object by taking slices, or by using Gauss's law to maybe first find the electric field, or in this case you can find the potential directly. But you can then go from the potential to the electric field, or from the electric to potential using this relationship in either case. So that's kind of what we got going on. Yeah, so it kind of gives you an overview of the different shapes that you might see. If you have questions, please ask.